Okay, we're going to pick up where we left off with the last video. This will finish off the notes for 4.2. It's going to cover pages 3, 4, and 5. Okay, so if you remember, we were talking about a random variable. And remember, a random variable is just some sort of numerical quantity that we want to study, that we want to analyze. Okay, so here they give us a probability distribution of a random variable. They don't tell us what y represents, and I think we should always, label what our random variables are. So let's say that y equals the number of bonus points you can get on an exam. Okay, so for example, I guess I can get either 2, 4, 8, or 10 bonus points on this test. Because remember, a probability distribution function lists every possibility and then ties to it the probabilities of each event occurring. So these are the only possible bonus points you can get on a test. You can get 2, 4, 8, or 10. All right, let's find the expected value of that random variable. If you remember, the expected value, that's just the mean, right? That's all that is the mean or the average. We tend to just call it expected value of this thing, the number of points we would get on the number of bonus points I'd get on an exam. Anyways, if you recall from the last video, the way we calculate expected value is we take each of the data values themselves, multiply it by the probability, and rinse and repeat that thing, adding them up down the chain. So I'm going to multiply these and keep adding them to the rest. All right, so I'm going to take 2 times the probability of getting a 2, which is 30%, plus the data value 4. There's a 40% chance I'm going to get a 4, so I'll multiply by 0.4. To get 8 bonus points, there's a 20% chance that's going to happen. And then I'm going to add up 10 bonus points. There's a 10% chance of that happening. If we add all these up together, we should get, what do we get? 4.8. Now be sure you can interpret what this number means, because it's not, big deal. You can get the number. That's good. But unless we understand what the number means, there's not much point in doing this. So remember, expected value, and this is why I like the word expected value more than mean. To me, it's more intuitive to what it really means. It's that if you were to take many, many, many exams, right? If you were to study many, many exam scores, I realize you can only get 2, 4, 8, or 10 bonus points on a test, but over the long run, after looking at a lot of them, all the bonus points that these exams get would average out to 4.8. So if you went into an exam, you would expect an average of 4.8 bonus points. Again, you can't get 4.8. You can only get 2, 4, 8, or 10, but that's what they all average out to. Okay, so maybe we could say over the long run, you would average 4.8 bonus points per exam. Okay. They also ask us to find the variance and standard deviation. So if we're looking for the variance of this random variable, remember the way we do this is very similar to what we did in Chapter 2. I take every data value and subtract it from the mean, or the expected value. Rather, I said that backwards. I'm taking the data value minus the mean from that, and then I square that result. Remember in Chapter 2 we squared them because sometimes you'd have things above the mean or below the mean. If you didn't square them, the sum always canceled out to 0. So we square that distance between the data value and the mean, and then we multiply by the probability of getting that data value. and I add all those up. So I keep doing that. I add data value minus the mean, square it, multiply by the probability, plus data value minus the mean, square it, multiply by the probability of that happening, and lastly, data value minus the mean squared times the probability of that data value happening. Now, that's not that hard once you get the pattern down. I mean, once you understand what you're doing, it's not hard to do. It's just subtracting, squaring, and multiplying over and over and over again. But it's a pain in the butt. So we're going to start to rely on some technology. I'm going to show you how to do this on StatCrunch. Maybe we'll do this example on StatCrunch once we finish this up. Anyways, if I did everything right earlier, this should come out to 7.36. Okay. Now, the last thing they want is the standard deviation. The standard deviation of this random variable. If you remember, the variance of some random variable is always equal to the square of the standard deviation, right? If you remember back in chapter 2, we had to square root all this mess to get the standard deviation because we wanted to undo all that squaring that we brought in, so we didn't have to worry about things canceling. So again, if I square these guys, they'll cancel and I'm left with just the standard deviation, and the standard deviation is equal to the square root of the variance. So this standard deviation can be found by taking the square root of that variance, which is about 2.713. And if you recall how we interpret standard deviation is the average distance that every data value is from the mean, right? I mean, the data value 2 is pretty close to the mean. The data value 10 is further from the mean. So every data value has some distance from the mean. Those distances average out to 2.7. Okay, so we could interpret that as over the long run, we expect the number of bonus points to be roughly 2.713 points away from the mean of 4.8. Over the long run, we expect the number of bonus points. To be about 2.7 points away from the mean, or on either side of the mean. Okay. Remember what you could do with things like standard deviation. You could use that to start thinking about outliers. We know we would expect the normal spread to be 2 standard deviations above and below the mean, so you can add 2 standard deviations to the mean and subtract 2 standard deviations and get an idea of the realm of a normal number of bonus points, or what would be considered abnormal. So let's do that. Let me show you how to do this on StatCrunch, because we really haven't done, I guess, much of anything on StatCrunch yet, but let me show you. So I've got it already up. When you have your spreadsheet up, here's what you're going to do. You're first going to type in to one of these columns your data values. So I could have gotten, let's see, 2, 4, 8, or 10 bonus points. And then in the column next to it, write down the probability of getting each event. So I'm looking at the notes here. To get 2 data values was a 30% chance. Or, I'm sorry, 2 bonus points. To get 4 bonus points was a 40% chance. This was a 20% chance, and this was a 10% chance. So then what you're going to do is you're going to go to Stat, Calculators. Okay, so let's open Calculators, and you're going to go down to Custom. All right, Custom is what we want. So you have 2 things you got to select: the values and the weights. The weights is what they mean by the probability. So the values, the data values, are occurring in column variable 1. That's what the default name is. So that's where the data values are. The weights, the probabilities they mean, are in column variable 2. That's all you do, compute. And look what they give you. They give you the mean, which is the expected value, 4.8 like we found. And they give you the standard deviation, just what we found, 2.713 if you round it. And then they've also got this probability calculator, which we're going to get into a little later, but we're going to use the dickens out of that thing. So StatCrunch can do those calculations really painlessly. And the further we go in stats, the more and more we're going to rely on this program to make our life a little easier. So let's look at the next example. Similar idea. So it says that a large auto dealership keeps track of sales made during each hour of the day. Let X equal the number of cars sold during the first hour of business on a randomly selected Friday. Based on previous records, the probability distribution of X is as follows. Okay, so let's make sure we understand what they're doing. The car dealership is tracking how many cars they sell during every hour of the day. They're collecting data on how many cars they sold. So we're assigning a random variable. Remember, that's just some numerical quantity we want to analyze. In this case, they want to analyze the number of cars sold during the first hour of business on a randomly selected Friday. And so instead of having to write that over and over and over and over again, we just call it X. That's the idea with labeling it, so we can be a little lazy and we don't have to write that all out every time. So what they've done is they've looked at all their old records and they've looked at how many cars they sold in that first hour. They either sold 0, 1, 2, or 3 in that first hour. And remember, the probability they find, that's just the relative frequency, right? They find how many times they sold 0 cars in that hour divided by how many data values they looked at. There's their relative frequency or their probability. So the first thing they say, is this a valid probability distribution? Well, remember, what does it mean to be valid? Two things have to happen. Do they all add up to 1? Right, so let's see. 0.3 and 0.4, that's 0.7, plus 0.2 is 0.9, and another one is 1. So yes, they do. So that's check 1. We're halfway there. All right. The next thing is, if you remember, all the probabilities have to be positive. Are all the probabilities positive? And we can see yes. So therefore, this thing is a valid probability distribution, because again, it shows that all the probabilities add to 1, so we're not missing anybody, or we don't have too much probability, and they're all positive. So they say use the calculator to interpret the expected value, or to compute it and interpret it, and same thing for the standard deviation. Well, let's go back to StatCrunch and do it that way. So I'm going to close this stuff up. Just going to open a new one. So again, in this first column, let's put the data values themselves. So they sold in that first hour on a Friday, they sold 0 cars, or 1, or 2, or 3. According to their records, that's what they did in that first hour. And then they found the relative frequency of each one, which ends up being the probability. So that's 0.3, 0.4, this was 0.2, and this was 0.1. Okay? So if you remember, you go to you go to Stat, Calculators, and then you're going to scroll down to Custom. And again, they want to know where the data value's at and where the probability's at. They call them weights. So the data values are in this first column called variable 1, and the weights, or the probabilities, are in this column called variable 2. Okay. By the way, you can click on these and change the names. That's just their default name. All you do is hit compute. So again, they give us the mean, which is the expected value, and the standard deviation, and then again a probability calculator, which we'll get into later. So the expected value is 1.1 and the standard deviation is 0.943. Expected value of this random variable is 1.1 and the standard deviation of this random variable was 0.943, I think. Yeah. Okay, so we found it, but again, big deal. We need to know what it means. So what that means is that over many Fridays, in that first hour of selling cars on a Friday morning, they can expect to sell an average of 1.1 cars. Again, they can't sell 1.1 cars. Sometimes they'll sell 1, sometimes they'll sell 3, sometimes they'll sell none. But on average, all those outcomes average out to 1.1 car per Friday morning in that first hour. And I mean, you better believe that's something the dealership wants to know and does know, right? Every major business does constant data tracking because they need to know, when is money coming in? When do we need to resupply? All this stuff. So it's very data driven. So let's say over many Fridays, or let's just say many Fridays, we can expect to sell an average of 1.1 cars in the first hour of business. Okay. Now how about that standard deviation? We found it. Remember, standard deviation, we get this idea that on a Friday morning, I might sell 3 cars. I might sell 0 cars. Every data value has some sort of distance from the expected value. And if you find all those average distances, how far on average each data value is from that mean, that is what the standard deviation is. So over many Fridays, the number of cars we expect to sell in that first hour will typically vary by about 0.94 cars from the 1.1 we expect to sell. The number of cars sold in the first hour will typically vary about 0.94 cars from the 1.1 we expect. Okay. So 1.1, if you were to add one standard deviation, which is the typical amount we would expect to vary, that puts you at about 2 cars. And if you subtract a standard deviation, you take 1.1 minus 0.94, you're getting close to 0 cars. So it's pretty reasonable to expect you're going to sell between 0 and 2 cars. Okay. This next example has something new to it, which I want us to go into a little more, and I might dig up some more examples, but I'm not going to put something like this on the test, not like this example. Something like, this example, perfectly fine for the test, and because you could do these by hand too. You don't have to have StatCrunch. We did a few examples by hand. They're not that bad. But this guy, I think I would just prefer to leave off. But let's take a look. It says in a lottery game, a player picks 6 numbers from 1 to 26. If the player matches all 6 numbers, they win $50,000. Otherwise, they lose $1. What is the expected value of this game? I mean, the first thing we should kind of think about our answer is the expected value should be negative, right? I mean, when you play the lotto, you should expect to lose. You're not, on average, you don't lose a lot, but the house has the edge, right? So for us, the people buying the ticket, we have a negative expected value. The state has a positive expected value. They expect to win a little bit each time on average. So really this is just an expected value problem, and to do an expected value problem I really just want to think of the probability distribution. So let's label a random variable. Let's say x is the amount of money I win. So I've got two options, right? I've got money 1. Or not two options. What I'm getting at is I want to list the money 1 and the probability of winning each amount, right? So here's the thing. I could win $50,000. That'd be great. Or I could lose $1. And if I were to lose $1, I should write that as a win of -1. Okay. Well, what makes this problem a little challenging at the moment is I need to know the probability of winning $50,000 and the probability of losing $1. So we have to go back to the rules of the game. It says that we pick 6 numbers out of the numbers 1 through 26, and if we match all 6, we win the 50 grand. So what we really need to figure out, we're going to have to come off to the side. We need to know how many ways are there to pick 6 numbers out of 26. And if you're playing the lotto, I don't think the order is going to matter. Like, it's as long as we get the 6 numbers. It doesn't have to be in a particular order. So let's just kind of say in any order. I just need to land on those 6 numbers. Doesn't matter which one I pick first. There's a lot more than you might be thinking. It doesn't seem like it would be that much, but actually there are a ton of combinations of ways to pick 6 numbers out of the digits 1 through 26. In fact, I use that word combinations. That's exactly what we're looking for. This is a mathematical thing known as a combination. And there's some symbols or formulas we can use to figure this out. So one way you're going to see it written is this way. You're going to see N choose R. That's a common way to write it. You also might see it this way, and you read it the same, N choose R. Okay, and here's the formula for it. It's N factorial over R factorial over N minus R factorial. That's the formula for it. And you might be looking at this factorial and going, what the heck is that? You know, it's not N, R, and N minus R. It's not an exclamation point. N factorial is defined as N times the number less than that times the number less than that, and so forth, all the way down to 1. So for example, 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1. So it's easy to calculate factorial. It's just a big number. It's just a lot of pounding on the calculator. So what we need to do is we want to find, the way this works is N is the sample size, or I'm sorry, it's not the sample size. N is the total possible numbers you have to choose from. So I've got 26 numbers to choose from. I want to choose 6 of them. That's how we read that. 26 choose 6. Okay. So technically speaking, it's 26 factorial times 6 factorial times 26 minus 6 factorial. It's a huge number. Think of 26 factorial. That's, according to the definition, it would be 26 times 25 times 24 times 23, 2, all the way down to 1. Take forever. So, but what this number will give us is it'll give us all the ways, or it'll tell us how many ways you can choose 6 numbers out of 26 numbers in any order. So some of these will be, well, here's what we're going to do. We're just going to go to Google and let it do it for us. So here's, your calculators can, a lot of scientific calculators can do this, and depending on your calculator, I'll help you find it. But you can also just go to Google and type N what the heck do I want to type here? How about n choose r? And if I scroll down, I'm going to find a combinations calculator. Okay, so I bet if you were to type in combinations calculator or n choose r calculator, you'll get it even faster. But let's just see what that does. See, there's that gnarly formula right there. And they're asking you, n is the number of objects. How many objects do you have? We have 26 objects. 26 numbers to choose from. And r is the sample size, how many we're going to pluck out. All right, it's going to be a big number. So let's see what it says. There are 230,230 different ways to pick 6 numbers out of a group of 26 numbers. There's a ton of them. So all that work to get that number, this was 230, 230. That is the number of ways that I can pick 6 numbers out of 26. Okay. So now I think I could figure out this probability, because if I'm talking about pulling off a win, these are the total number of lotto tickets I can grab. Right? That's the total number of lotto tickets or combinations there are out there. Only one of those is a winner. So the probability of getting that 50,000 is 1 out of that many tickets. All the rest are losers. Okay, all the rest are losing tickets. So out of those 230,230 tickets, all but 1 are losing tickets. They're going to make me lose $1. So 230,229 of them are losing tickets. So remember, probability is just the number of ways to pull off that event over how many events there are. So there's that many ways to lose over that many tickets. That many ways to win over that many tickets. There's the probability. And now that I have that, the expected value is not hard. The expected value of x, remember, you just take the data value times the probability of it occurring. So 50,000 times 1 over 230, 230. Plus, I've got a -1 times this probability. If I did it right, this is what I get. -0.78. Remember, that's the expected value to us, the person playing the lotto. So what that means is, on average, every time you play the lotto, you can plan on losing 78 cents, right? And it doesn't mean you lose 78 cents every time. Every time you lose $1. You can't lose 78 cents, you lose $1. But maybe you lose $1 twice, 3 times, and then you win a ticket. You win, $3 or $4. So it averages out, it balances out to a loss of 78 cents every time you play that lotto. In the long run of playing the lotto, or this lottery, you can expect to lose 78 cents each time. Each time you play. Okay. So again, it's a good problem, and depending on how much time we get to spend talking about this other idea, it might be test worthy, but I don't think we're going to get to spend a lot of time with it. That's why I'm just leaning towards no. There's plenty of other good questions we can ask out of here. So just let's not stress about this one for the test. But I believe the homework has 1 or 2 like it. All right, let's look at the last page. I actually want to make one up very similar to this before we do this one, okay? Because this one is the harder of the 2 examples. So I'm literally going to do the same scenario here next to it. So it says a company estimates that 3% of their products will fail after the original warranty period, but within 2 years of the purchase with a replacement of $150. So I'm keeping all that the same. If they want to offer a 2-year extended warranty, this question says what price should they charge to break even? For now, I'm going to say no, I don't want to do that. I'm going to hijack this problem. Let's come over here. And let's say they sell a 2-year warranty for $5. That would be 50. Let's say $5. Okay. What is the expected value to the company? Expected value to the company. You know, when they sell you a warranty, they're not doing it for your best interest. They're making money off the deal, or they're not doing good business. So this is just another expected value problem. So let's label a random variable here. What is it I'm trying to figure out? I want to say, let's let x equal the amount of money coming into the company. Because I want to find that expected value, the expected value of how much money the company can expect to get in, the mean, all right, from each transaction. So again, for my probability distribution, I'm going to list all the possible outcomes that can occur, okay, and I'm going to list the probability of each outcome occurring. Now, two things happen here. Either the product does not fail, okay, and if you buy a warranty for $5 and the product doesn't fail, in other words, you don't cash in on the warranty, then you're just down $5, okay? So that can happen. Let's just write that down. If you are down $5, the company is up $5. They made $5 off you. But 3% of the time, their item is going to fail, and they're going to have to shell out $150 to replace it or to fix it. So 3% of the time, the company is going to be out money. Now, they have to shell out $150, but didn't they already take $5 from you? Like to buy the warranty, they took your $5. So really, they're only out $145 if their product fails. Okay. Now, we already have it. The probability that their product fails is 3%, so that's 0.03. And those are complement of events. The product fails or it doesn't fail. So if there's a 3% chance it's going to fail, there's a 97% chance it does not fail, and they just get to keep your $5. So a vast majority of the time, they just pocket the $5. 97% of the time, they pocket $5. 3% of the time, they take a loss of $145. So let's see what the expected value is here. What does the company expect to do with this? Win or lose, and by how much? So the expected value, again, is the event times the probability of it happening plus the event times the probability of it happening. Hold on a second. I don't have a calculator here. Okay, I had to pause it to go find a calculator. This comes out to 0.5. That's my expected value. So with all their warranty selling business, for every warranty they sell, they can expect to come up a positive $0.5, 50 cents. So over the long run of selling many warranties, they average 50 cents profit per warranty. Okay. So this next, or the problem I skipped, is the same idea, except they've changed it slightly. So let's bring this back in now. Let's do this problem. Okay, so a company estimates that 3% of their products fail after the original warranty period, but within 2 years of purchase. The replacement cost for the company is $150. Now, here it's saying if they want to offer a 2-year extended warranty, what price should they charge so that they'll break even? In other words, what price should they charge so the expected value is 0? So on the problem I made up, I told you the price they charged and I asked for the expected value. Here, they are telling you they want the expected value to be 0. They want to break even. So what price should they charge? Okay. Well, it's the same idea. I'm going to say, okay, X is the amount of money into the company. Okay. And we want the expected value of that thing to be X, or I'm sorry, to be 0. We want to break even. Okay. They're not going to make profit. They don't want to lose money either. Let's write out what can happen. Now this is where it's a little bit different. Again, I'm going to write every outcome that can occur and the probability of each outcome occurring. Okay, well, kind of just following our example, 3% of the time their product is going to fail, and 97% of the time their product is not going to fail, and they pocket the money. I need to use a variable for the money here, so why don't we say let's let C equal the cost of the warranty. Okay, C is the cost of the warranty. So doesn't that mean that 97% of the time, whatever C is, whatever that cost is, they keep it. They just get to pocket that money. Okay. However, 3% of the time, they have to shell out $150. 3% of the time, their product fails, and they're out $150. Well, they're out $150 aside from whatever they took in. So remember, what's going to happen is they're going to take your money, whatever it is, and then from that, they're going to be out $150. Now again, we want the expected value to be 0. So expected value is always the outcome times the likelihood of it happening, or the probability, plus the outcome times the likelihood of it happening. And that's the expected value, and they told us they want us to get that thing to 0. So what we've done is we've created a linear equation that I can then go solve for C. So this would be 0.97 times C plus, and what I'm going to do here is I'm going to distribute this 3%. So I get 0.03 times C minus 0.03 times 150 should come out to 4.5. If you notice, these guys, they add up to 1C minus 4.5 equals 0. So I get C, and move this to the other side, I get 4.5. That's the cost of the warranty, right? C is the cost of the warranty. So for them to break even, they should charge $450 for the 2-year warranty. Charge $450 for the warranty. Okay. Just a little note, when you're solving an equation, one thing that really helps is lock down your equal sign. Keep them lined up. When you line up your equal signs, it forces you to just be a little bit more organized. Okay, so that's one little trick that you can use to help keep your work a little neater. Okay, well, that is it for up to 4.2. I'll get another video going shortly covering 4.3. All right, thanks.